In this video, we will talk about logarithm functions. Log functions are used in many applications, including maximum likelihood estimation and the transformation of variables that exhibit large positive outliers. In a previous video, I talked about the transformation of variables. Logarithm functions have nice properties that can be used to simplify mathematical problems, in particular in optimization. These properties stem from power functions and inverse functions. Let me just illustrate these properties. Let A and B be parameters that are element of R. Then the following properties hold for log function. Note that I refer here to the natural logarithm because that's the most commonly used logarithm, which has E as its base. So ln A times B can be written as ln A plus ln B. Ln A divided by B can be written as ln A minus ln B. Finally, ln A to the power of B can be written as B ln A. Now, these properties are frequently used in calculations, and we will come across them several times in this course. All of these properties can be derived if you wish. Again, if you have any questions, just leave some comments below. Next, I would like to show you how to plot functions using Python. We have to import the NumPy and the matplotlib package. Next, we use the linear space function in NumPy. So I refer to np to go into the NumPy package, take linspace. It has a minimum value which has to be positive because the ln function is not defined at 0. And if we approach 0 from above, we of course tend to minus infinity, so you have an asymptotic behavior. The maximum value, I put this at 10, and then I have maybe 1000 steps in between. So that will create a NumPy array, starting from a minimum value, going all the way up to the maximum value, and it will take 1000 equally spaced steps. And here is my array. We have here the minimum value, and it goes all the way up to the maximum value, and we have exactly 1000 steps. Again, as you should know, Python counts from 0. Next, we define our y value, which of course refers to the natural logarithm. Now, the tricky thing in NumPy is it is denoted with log, not ln. Line 10 takes the array x and applies the ln function and provides the array y, which takes the values. So if we run this, we now have the values of ln x in this range. So here I specified the title of my figure. I put in labels for both axes. Then I use the plot function. I save this figure, which is convenient if you want to use it maybe in a LaTeX document or a Word document or PowerPoint. I specify a resolution, but of course that you can modify if you want to store larger figures, and then I use the plt.show to see the figure in my integrated development environment. I'm now running this one more time, and here we have the function. Now, this is a very nice way to plot functions in Python, and of course we can modify this for any other function. Now, as I mentioned at the beginning, the ln function is used quite frequently in optimization problems. I now want to illustrate why that actually works. What we have to understand is that the ln function is a positive monotonic transformation. Now that means that it doesn't change the order. So by preserving the order, the nature of the extrema of the function, so the maximum, the minimum, are not changed. As you should know from your school days, if we optimize a function f of x, we obtain a first order condition as f prime x is equal to 0. And when we solve this, we might be able to find an x star where this condition is fulfilled. This x star would be an extremum of the function. Now, if we apply an ln function to f of x, we can first explore how this affects the first order condition. So that's one step. We also have to note that at this extremum, the nature of it is determined by f prime prime, the second derivative, at the point x star. So whether this is positive or negative, that will determine whether we have a maximum or a minimum. Now, when we apply the transformation, let's have a look how this affects our first order condition. So the ln of f of x, we take here the derivative with respect to x, we apply the chain rule, so we obtain 1 divided by f of x, and then I differentiate f prime x. Now it's important to note that for the log transformation to be valid, f of x has to be always positive. The next thing to note is for this condition to be equal to 0, the only thing that matters as before is whether f prime x is equal to 0. The denominator doesn't matter in this setting. In fact, of course, it can't be equal to 0 for obvious reasons. So put differently, the first order condition is not influenced by the log transformation. Now, if we now go further and take the second derivative, what happens there? So this, of course, leads to the quotient rule. So we obtain f of x, f prime prime x, minus f prime x times f prime x, and then divided by f of x to the power of 2. Now we are interested in this expression assessed at x star. We know at x star f prime x star is equal to 0 because the first order condition is fulfilled. Now if we write this again assessed at our extremum, so x is equal to x star, then obviously it simplifies to f prime prime, the second derivative, at x star divided by f of x. And obviously the sign only depends on the numerator, because we know f of x is positive. Yeah, you see, by applying the ln transformation, it doesn't change the nature of our extremum, so we can use that if it makes sense to simplify our calculation. And you will see in data science settings, it is very frequently helpful to apply log transformations. Very often we have quite complicated products which simplify to sums after taking the log transformation. Good, I see you in the next session.